We often think about environmental crises, the big dramatic ones like floods or fires. But sometimes the biggest threats are quieter, almost invisible.
Mm.
Think about the ground beneath our feet. In places like Lesotho, the mountain kingdom, this silent crisis, soil erosion, it's not just about losing dirt. It's a direct threat to people's lives, ecosystems, infrastructure.
That's absolutely right. It might not grab headlines daily, but that slow, steady loss of topsoil, it has these massive long-term consequences. We're talking about the very foundation of agriculture, water health, landscape stability. It's fundamental.
And that brings us right to the mission for this deep dive. We're going to explore how really cutting-edge tech, specifically machine learning smarts combined with incredibly detailed geospatial data, is being used to understand and maybe fight this challenge in Lesotho.
Yeah, imagine using computers, intelligence systems, to predict where the land is most vulnerable, and crucially, figure out how we might protect it.
Exactly. Our guide here is a really fascinating project report you shared. It's called Machine Learning-Based Prediction of Soil Erosion for UWSII in Lesotho, dated May 2025.
Right, it's a deep dive in itself, really. It outlines this innovative system designed precisely to tackle this issue.
Okay, so think of this as your fast track. We're going to unpack the key insights from this report, aiming for those aha moments, but, without drowning you in technical jargon.
Oh, good.
So let's start by painting a picture. Why Lesotho? Why is soil erosion such a critical problem there specifically?
Well, Lesotho's geography is unique and makes it really susceptible. It's extremely mountainous, lots of steep slopes. That naturally means a lot of water runoff.
Okay, steep terrain equals fast water.
Exactly. Then combine that with intense seasonal rain.
Yeah.
Most of their rainfall happens in short, heavy bursts. It's like a perfect storm for soil loss. Think of a water slide, steeper, longer, more water.
And the more stuff gets washed away. That's a powerful image. All that water rushing down has to take something with it.
Precisely. And the soil itself, unfortunately, in many areas, is quite fragile. A lot of the underlying rock is sandstone. It breaks down fairly easily.
So the topsoil is vulnerable right from the start.
Very vulnerable. And then on top of that, you have some land use practices over time, things like overgrazing, maybe some deforestation historically, certain farming methods that have, well, unfortunately made things worse. So it's this mix, nature and human impact.
Right, the sort of unfortunate convergence of natural vulnerability and human activity.
Yeah.
What does all this disappearing soil actually mean for the people, for the environment there?
Oh, the consequences are really significant, huge. For most people who depend on farming, you see declining crop yields, you see growing food insecurity. It's a major socioeconomic hit.
Less fertile soil, less food, direct impact on livelihoods, contributing to poverty.
It's a direct hit, yes.
Hmm.
And it goes beyond farming. Ecologically, we're seeing degradation of vital wetlands. Over 30% in Lesotho are affected by this sediment runoff.
30%, wow.
Yeah. Rivers get clogged with sediment. That harms water quality, aquatic life. And maybe most critically, it impacts the Lesotho Highlands Water Project. That's a crucial water source for the whole region.
How does it impact the water project?
The reservoirs start filling up with eroded soil. Siltation, basically, reduces how much water they can hold, threatens their long-term function, so the effects just ripple outwards.
So it's not just losing dirt in a field. It cascades through the ecosystem, hits vital infrastructure. The report mentions dongas. What are those exactly?
Dongas. They're a really stark visual sign of severe erosion in Lesotho. Imagine these huge gully systems, almost like mini canyons.
Mini canyons, how deep are we talking?
That can be 10, even 15 meters deep. These aren't small ditches. This is permanent loss of farmland. They carve up the landscape, make it hard to move, and they act like channels, speeding up sediment flow into rivers. A very visible scar.
10 to 15 meters, that's like losing several floors of soil. Okay, so we get why Lesotho is the focus. Now, the report talks about a traditional approach called RUSLE. What is that?
RUSLE stands for Revised Universal Soil Loss Equation. It's a well-established method, kind of like a recipe, really. It's used to estimate the average amount of soil lost each year.
Okay, but specifically from certain types of erosion.
Yes, from what we call sheet and rill erosion, the more sort of uniform washing away of soil from surfaces, not those deep dongas.
Yeah.
It's been a standard tool in soil conservation for, well, decades.
A recipe using science and real-world data.
Exactly. RUSLE uses a formula with 5 key ingredients, or factors. First is rainfall erosivity, the R factor. Measures the power of rain to cause erosion, how intense, how long it lasts.
Okay, so those intense Lesotho downpours mean a high R factor.
You got it. Second is soil erodibility, the K factor. That tells us how easily a specific soil type gets detached and moved by water. Soil texture matters a lot here. Sandy soils tend to go more easily.
Makes sense. Next ingredient.
Third, the topographic factor, LS factor. This looks at the shape of the land slope length and steepness. Longer, steeper slopes mean faster water, more erosion. Hugely important in mountainous Lesotho.
No surprise there. Factor 4.
Fourth is cover management, the C factor. This reflects how ground cover, forests, crops, whatever, and land management affects erosion. More plants generally mean better protection.
Right, more vegetation holds the soil. The report mentions NDVI here.
Yeah, NDVI, Normalized Difference Vegetation Index. It's like a satellite's view of how green and dense the vegetation is, often used to help estimate this C factor. Greener usually means less erosion.
So healthy vegetation means a lower C factor, better protection. And the last one.
Fifth is the support practice factor, P factor. This accounts for conservation practices on the ground, things like terracing, contour plowing. Effective practices lower the P factor, meaning less erosion.
Okay, so you plug in these 5 factors, R, K, L, S, C, P, and RUSLE gives an estimate of annual soil loss. The report mentions using this with GIS. How do maps fit in?
GIS, Geographic Information Systems, are perfect for this. They handle spatial data. Each of those 5 RUSLE factors can be a map layer.
Ah, like stacking transparent maps on top of each other?
Exactly. GIS lets you overlay these layers, do the USLE calculation for every little square of land, basically, and create a final map showing where predicted soil loss is high or low across a whole region like Lesotho. You get a detailed picture, not just one number.
So you can pinpoint hotspots. That's a big step up. But RUSLE has limits, the report says. What doesn't it tell us?
Yeah, while it's great for that sheet and rill erosion, it doesn't really model other types well. Those deep dongas, riverbank erosion, landslides, RUSLE doesn't capture those.
Okay.
And it gives an average annual loss. Doesn't tell you about specific extreme events like one massive storm. Plus, it needs good data for all 5 factors, which can be a challenge to find everywhere.
Right. Getting all that accurate info can be tough. Okay. Traditional approach understood. Now, the upgrade. Google Earth Engine, GE. What is that and why use it here?
Think of GEE as this giant cloud-based warehouse. It's packed with satellite images, geographical data, and linked to really powerful computing resources. It lets researchers access and process huge data sets, things you just couldn't handle on a normal desktop.
So less downloading massive files, more processing in the cloud?
Pretty much. For this Lesotho project, GEE was super helpful. They used it to get all the map layers needed for RUSLE, satellite imagery for vegetation, elevation models for slope.
Made getting the inputs easier?
And much easier. And calculating slope across the whole country, deriving that NDVI vegetation index from satellite data, GEE handled that. Crucially, it also helped harmonize data from different sources, different resolutions, making them all work together.
Okay, so GEE streamlined the data prep for this big-scale analysis. Now, the really exciting part, machine learning. The report focuses on CNN's convolutional neural networks. What are they? How do they go beyond RUSLE?
Right. Machine learning generally is teaching computers to learn from data without explicit programming for every single step. They can find really complex patterns, nonlinear relationships that traditional models might miss.
Okay.
And that's valuable for something as complex as soil erosion. CNNs are a specific type of machine learning, especially good at spotting patterns in images. Think facial recognition on your phone often uses CNNs.
Right. They see features and learn what they mean, like edges, textures.
Exactly. Here, the images are the map layers, rainfall, slope, vegetation, soil type stacks. The CNN learns to see patterns in these layers associated with high or low soil loss.
So it's learning the visual cues for erosion.
Essentially, yes. It can potentially grasp those complex interactions between factors and integrate diverse data more effectively than a fixed formula like RUSL. It offers this powerful lens.
What are the specific advantages, then, using ML here?
Well, handling those nonlinear relationships is key. It can also potentially incorporate a wider range of data, maybe things not even in the RUSL equation, but still relevant. And importantly, once trained on past data, these models can forecast future erosion patterns. RUSL doesn't easily do that.
That predictive power sounds incredibly useful for planning, for prevention. The report says they train the CNN on RUSL outputs. Why do that?
Ah, that's a clever approach. RUSL gives us a scientifically grounded estimate of soil loss, right? By using those RUSL estimates as the ground truth for training.
The correct answers for the ML model.
Exactly. The CNN learns the underlying spatial patterns in the environmental data that lead to those RUSLE predicted erosion levels. Then, it can potentially refine those predictions, spot subtle patterns RUSLE misses, or crucially, project trends forward based on changes in input data like rainfall or vegetation.
Okay, so it's like using RUSLE's science as a teacher for the more flexible machine learning model. Got it. Now, how did all these bits, RUSLE, GE, CNNs, fit together? The report describes a layered approach for the system.
Yeah, they organize it logically into 4 layers. Top layer, presentation. That's the face of the system. The web interface users see maps, charts, reports, what you actually interact with.
What the user sees. Okay. What's under the hood?
Below that, the application layer, kind of the system's switchboard. It handles communication between the user interface and the technical bits. They used Flask, a Python tool for web apps, to build an API, basically. Rules for how different parts talk to each other. You click a button, this layer figures out what needs to happen.
So it translates user requests into actions for the system.
Precisely. It might then talk to the model layer. This is where the actual erosion calculations happen. It holds both the RUSL model for baseline estimates and the trained CNN model for those advanced future predictions, the heavy lifters.
The calculation engines. And the base.
The bottom is the data layer. Everything is stored. They used a MySQL database with PostGIS extensions. Those are special tools for handling geographical data efficiently, storing area boundaries, prediction results, that sort of thing.
So a well-structured stack. Presentation, application, model, data, each doing its job. The report gets quite specific about the data used for predictions. Can you give us the highlight?
Sure. For each RUSL factor, they use specific data sets, mostly via GEE. For rainfall erosivity, they used CHIRPS data. That's a blend of satellite info and ground weather station data. Goes back to 81, about 5 kilometers resolution. They used a specific formula to get the R factor from annual rainfall.
Okay, chirp yes for rain. Good blend. What about soil erodibility? K.
For K, they chose Open Land Maps soil texture data, finer resolution, 250 meters. Chosen because it seemed to represent Lesotho's specific soil variations better than some global options, more locally tuned.
Better local fit. And topography, LS, the slopes.
SRTM digital elevation model for that, 30-meter resolution. Gives detailed terrain info needed for slope length and steepness calculations. They used a specific formula by Desmet and Govers, known to work well in complex hilly areas like Lesotho.
Got it. And cover management, see, that's the vegetation index, NDVI again.
Exactly. They combine data here. High-res Sentinel-2, 10 meters for recent periods. MODIS, 250 meters going further back. Even older Landsat 5, 30 meters. This gives a view of vegetation changes over time.
Clever use of multiple satellites.
Yeah. Then they use a specific formula calibrated for Southern Africa to convert NDVI values into the C factor, making it more relevant regionally.
Smart. Finally, the support practice factor, conservation efforts.
That was trickier. There isn't a ready-made map of conservation practices across Lesotho, so they estimated it based on slope steepness. The assumption being flatter areas might be more likely to have conservation measures. Steeper slopes, maybe less so.
An estimation, then.
An estimation, yes. The report acknowledges it's not perfect, but argues it was better than simply ignoring the factor or guessing randomly.
Okay. It sounds like really careful data selection, considering resolution, time period, local relevance. Let's dive into that machine learning model a bit more. We know it's a CNN. What exactly did it learn? How was it trained?
Its main job was predicting erosion severity, pixel by pixel, by learning spatial patterns. The input wasn't just one map, but a stack multiband rasters. Rainfall, elevation slope, NDVI, soil type.
Like layers in Photoshop, but with environmental data.
Kinda, yeah. They standardized the data, first to put everything on a similar scale. And because the area is large, they broke the maps into smaller tiles, manageable chunks.
Tiles, okay. And the model architecture.
The core used a pre-trained encoder VGG16, or ResNet. These are well-known models, already good at picking out features from images. Think of it as giving the model a head start on understanding visual patterns.
Using existing knowledge.
Exactly. This encoder was followed by a regression head. That part takes the features the encoder found and learns how to link them specifically to soil loss values.
And how did they teach it that link, the training?
They use the RUSLE model's outputs as the ground truth, the right answers. The CNN's goal was to predict values close to those RUSLE estimates. They use mean squared error to measure the difference, guiding the learning.
Okay.
An optimizer called Atom helped fine-tune the model's internal settings. They use a dynamic learning rate adjusted during training. And importantly, k-fold cross-validation and data augmentation like flipping images to make sure the model generalized well Didn't just memorize the training examples.
Right, helps it learn robust patterns. So it connects visual data patterns to RUSLE's predicted erosion amounts, the output being a detailed erosion map. Why CNN specifically for this, not some other ML model?
CNNs excel with spatial data like maps. Their structure lets them process information in local pixel neighborhoods. They see context. That's crucial for erosion. It depends heavily on the surrounding landscape.
Other models don't capture that spatial aspect as well?
Not inherently, no. Models like random forests or SVMs don't naturally process spatial relationships in the same way. CNNs also learn hierarchical features, simple edges to complex landforms. And they're built for pixel-wise prediction, generating those high-res output maps. They're just a really good fit for this kind of geographic image analysis.
Okay, the spatial awareness and detailed output makes CNNs the right tool. Now, having this powerful prediction is one thing, making it usable is another. How did they make this info accessible?
We built a web-based application, a user-friendly front end to see the predictions, explore interactive maps, download reports, designed with different user roles too, standard users, experts, admins, each seeing what they need.
Tailored access. What can you actually do in the app?
There's a dashboard for an overview. Then the map viewer, that's key. You see the erosion predictions on a map, zoom, pan, turn layers on-off like the raw input factors of the final prediction. There's a legend. Area selection, visual exploration is vital.
Absolutely. Seeing is understanding. What about deeper analysis?
That's the report viewer editor, especially for experts. They can write detailed analyses within the app, linking text to specific predictions, has formatting tools, and can generate downloadable PDF reports combining text, maps, charts. Even tracks report versions. It connects prediction with interpretation.
So it supports the whole workflow, from data to shareable insight, and for system managers.
An admin panel for user management, permissions, maybe other site content. The report also stresses they applied good human-computer interaction principles, HCI, things like progressive disclosure, clear feedback, error prevention, consistency, data export, making it usable, not just powerful.
Sounds like they've really thought about the end-user experience. What about testing? How did they check if it all actually worked?
A multi-pronged testing strategy. Unit tests checked individual code pieces, like a specific calculation function. Functional API tests checked if different parts communicated correctly. Could the web front end properly get data from the back end?
Testing the connections.
Yes. And crucially, comparing the ML model's predictions against the RSLE estimates, the ground truth, to gauge accuracy. Plus, usability feedback from potential users.
Covering all the bases, the report mentions a specific tool, CRER.py. What was that for?
That was a Python script specifically for validating the ML model. It loaded the trained model, ran it on unseen test data, and then visually compared the model's predicted map with the corresponding RUSLE map for that same area, side-by-side visualizations.
A direct visual check of performance.
Exactly. Lets you see immediately where the model agrees with RSLE and where it might differ. A clear assessment.
And the results. How well did the ML model do in these tests?
Pretty well, it seems. The training and validation losses decreased nicely during training, suggesting effective learning without overfitting. On the separate test data, the mean absolute error, MAE, was 0.0848, which means it's a relatively low error number, suggests the model's predicted soil loss values were, on average, quite close to the RUSLE estimates. Visually, the prediction maps align well with RUSLE, especially in pinpointing high-risk zones. And it seemed to pick up on increasing erosion trends in known degraded areas.
That's really positive. The ML seems to be learning effectively and giving reasonably accurate results.
Yeah.
So wrapping up, what's the big takeaway here? And what's next?
The big takeaway is that, yes, it's definitely feasible to integrate these diverse data sources, train ML models like CNNs, and generate useful soil erosion predictions for a place like Lesotho. They build a functional system that makes these predictions accessible via maps and reports. That's a solid achievement for supporting decision-making.
But there are next steps.
Yes. They acknowledge the full early warning system aspect wasn't completely implemented in this phase. That's key future work.
Okay, so the warning part needs more development. What else is planned?
Several things. Exploring a hybrid GIS approach, maybe ArcGIS for fine-scale local work, GEE for national scale. Improving the underlying RUSLE model itself by incorporating local field test data from Lesotho, making the web app even better usability, image resolution, interactivity.
Refining the tool and that early warning system.
That's a major focus, fully integrating it. Setting erosion thresholds, automating alert generation using near real-time GE data, building a notification system, email alerts, maybe other channels to get warnings to the right people quickly. They even detailed database plans for notifications.
Sounds ambitious. Anything else?
Enhancing system security, expanding the data inputs, maybe climate projections, other vegetation indices, basically making it a more comprehensive, robust, and proactive tool for land management.
It really sounds like a project that's made significant strides on a complex problem with a clear path forward to make it even more impactful.
Absolutely.
Yeah.
It's a powerful example of combining established science like ROSLE with cutting-edge tech ML, cloud computing, for environmental monitoring, proactive land management, not just in Lesotho, but potentially many similar vulnerable regions globally.
So as we close this deep dive, it really underscores how these data-driven approaches can tackle major environmental challenges. It's not just about understanding the problem anymore, is it? It's about building tools to predict and hopefully prevent the worst outcomes.
Indeed. And this work is a compelling reminder of that ongoing need for innovation, for collaboration, to protect our planet's essential resources. It's about using the best tools we have,